The focus on 2.4 is absolute value functions. In your textbook, they go into more graphing of absolute functions, and then they also cover solving equations and inequalities with absolute value functions. I feel that we've done enough graphing of absolute functions in our prior sections, so my focus here will just be on the solving of equations with absolute values and inequalities with absolute values. So what may come up as you go through solving are these properties of absolute values that I'd just like to review. If we look at property 1 and property 2, those are basically properties where you can either do the absolute value first and then the operation, or the operation then the absolute value. So in property 1, you notice that you can either multiply first, then take the absolute value, or take the absolute value and then multiply. 2 is with division. You can divide first, then take the absolute value, or take the absolute value first, then divide. Property 3 is just a generic property that says the absolute value of a positive is equal to the absolute value of the negative. So you think about something like absolute value of 2 and absolute value of negative 2. They're both equal to 2. The fourth property I would like to touch on, you won't be using that, but it's more a cautionary property, that when you talk about addition with absolute values, there's no equality. It can be equal, but basically if you take the absolute value first and then add, that's not necessarily going to equal to the addition first, then the absolute value. It could be, but it could also be larger than. So a real quick example would be if one of those values was negative and one is positive, let's just say that we wanted to take the absolute value of negative 2 added to the absolute value of 3. Well, that's going to be equal to 2 plus 3, or 5. However, if you take the absolute value of negative 2 plus 3 and do the addition first, you get the absolute value of 1, which is 1. So you see these are not equal. So when you take the absolute value first with addition, it's either going to be equal or greater than if you took the absolute value after you do the addition. So let's really quickly look at where we get our equation for our absolute value. And we'll look at this very simple example where we have x equal to negative 4. So when we think about that, the x's that will make this equation true would be if x is equal to positive 4, or if x is equal to negative 4. Those are our solutions. And basically what we're saying with an absolute value, and the reason why it's never negative, is because an absolute value is the distance from 0. What this equation is saying, it's saying, find me all the x values that are 4 units away from 0. Ooh, I need an O on that. So if we look at this graph, we can see that if we start at 0 and we go 4 units to the right, we're at positive 4. If we go 4 units to the left, we're at negative 4. So to get rid of an absolute value, oftentimes you'll have both a negative and a positive solution. And this is actually where our equation for absolute value comes from. Whenever you have an absolute value equal to some positive number, so this is going into our solving of equations. So let's say you have some absolute value, we'll put u in there, and it's equal to some value k. But here k needs to be positive, as in our absolute value of x equal to 4. Then to get rid of the absolute value and solve the equation, you're going to set it up to equal to the positive k or equal to the negative k. Let's go ahead and practice this. In example 1, we want to solve the absolute value of 3 minus 4x equal to 7. So here our u is everything inside the absolute value, which would be the 3 minus 4x. And our k is 7. So since 7 is greater than 0, so our k is greater than 0, then we can use this property that says, oh, okay, then I can get rid of my absolute values by breaking this up into two pieces, where I'm going to set 3 minus 4x equal to 7. Whoops. Erase that. So 3 minus 4x equal to 7, or 3 minus 4x equal to negative 7. So what's inside the absolute values has to equal positive 7 or negative 7. And then we would just solve these equations separately. If I were to subtract 3 from both sides, I would get negative 4x is equal to 4. And then dividing by the negative 4x equal to 4 over negative 4 would give me a negative 1. So that's one possible solution. Solving the next equation, subtracting the 3 from both sides, I get negative 4x is equal to negative 10. And then dividing both sides, and I usually don't show this step, I just do it. By negative 4, I get x is equal to the negative 10 over negative 4 will reduce to positive 5 halves, or 5 over 2. So these are two solutions, and we can check. If you go back to the equation and you put in x is equal to negative 1, you get 3 plus 4, which is a positive 7. So the first one checks out. If you put in 5 halves, that would be 3 minus 20 over 2, 3 minus 10. So you'd have a negative 7, absolute value is positive 7. So that solution checks out as well. And now remember, normally when we write solutions, we'll write it as a solution set. So we'll use our set braces and write negative 1 comma 5 halves. So the key is to get the absolute value by itself on the equal sign and see if it's equal to a positive number. If it's equal to a positive number, then you can split it up. Example B, well, I don't know if I can use this property because I don't have the absolute value by itself. So the first thing I want to do is subtract 11 from both sides. Don't forget your order of operations. So I get negative 2 times absolute value of x minus 5 is equal to negative 4 if I subtract the 11 from both sides. And now remember, to get the absolute value by itself, we're going to divide everything by the negative 2. So that will cancel. And again, I normally don't show this step, but it's a good review. Now I have the absolute value of x minus 5 is equal to positive 2. Absolute value equal to positive number can split it up into x minus 5 equal to 2, or x minus 5 equal to a negative 2. And then adding 5 to both sides, I have x is equal to positive 7, or x is equal to positive 3. Again, I could put in 7 and 3 and check, and I'll find that it will work. It'll equal to 7. And those would be my solutions, 7 and 3. There are some special cases. So the question comes up, what if the k value is not positive? And then we have these two situations. The first one says if k is equal to 0, there's only one solution. And then if k is less than 0, so it's negative, we have no solution. And these should make sense once we go through them. In example 2, we want to solve the equation absolute value of 5x minus 1 equal to 0. If I were to break it up, now I can't use that property because my k value here, which is 0, it's not greater than 0, so I really can't use the property that we were using before. However, if I did try to use that property and just set this equal to the positive 0 and equal to the negative 0, positive 0 is 0, negative 0 is 0. So really all you're doing is you're trying to figure out when 5x minus 1 is equal to 0, because the only solution is the absolute value of 0. That's our only solution here. Setting 5x minus 1 equal to 0, I end up with x equal to 1/5. After solving, now I could put 1/5 in and I'll see that that will work. 5 times 1/5 is 1, 1 minus 1 is 0, absolute value of 0 is 0. and that would be our only solution. So again, if you have an absolute value equal to 0, there will be just one solution. It's whatever makes whatever's inside the absolute value equal to 0. However, if you have an absolute value where you have it equal to a negative number, the absolute value is a distance. It is never negative. So it doesn't matter what x values I put in, this will never be equal to a negative number. So it doesn't matter what negative number it is, there's no solution. And I don't have to do any work for that. Well, let's move on to another type of equation that you may see with absolute values. What, instead of having an absolute value equal to a positive number, what if instead we had the absolute value equal to an absolute value? The idea is still the same. Both the positive and the negative solutions for, in this case, our u and our v, need to be the same. And it could be negative or positive because the absolute value will make them both either 0 or positive. So what you're going to do is just hold the first equal to the second, hold the first equal to negative of the second. So u equal to w, u equal to negative w. In example 3, and we'll just do one example like this, we have the absolute value of 3 minus 5x is equal to the absolute value of 2x minus 9. So again, we're trying to find the x's that make this true, and what's in the absolute values can be negative or positive or 0 as long as they're the same expression inside. And one could be negative and one could be positive because, again, we're taking the absolute value. So the 3 minus 5x, that would be our u. 2x minus 9, we could look at that as our w. And I could split this up, oh, maybe I'll do it under here, into keep the u, so that would be 3 minus 5x equal to keep the w, 2x minus 9, or keep the u, 3 minus 5x, equal to the negative of everything inside the absolute value, so parentheses 2x minus 9. So just be careful with your use of parentheses. And now we'll go ahead and solve these equations separately. So again, the goal is to get rid of the absolute value so we can solve and use all of our properties from algebra. I think I am going to add the 5x to both sides so I can get a positive 7x. And then when I add 9 to both sides, I get 12 equal to 7x. So dividing by 7, I have 12 over 7 is equal to x. And we could put that inside for x in the original equation, and it will come out that they're equal. So the 3 minus 5x equal to negative 2x minus 9, the first thing I want to do is distribute that negative to get negative 2x plus 9. And in this case, I think I will also add the 5x to both sides so I can get a positive 3x on the right. So 3 equal to 3x plus 9. And then when I subtract 9 from both sides, I get negative 6 is equal to 3x. Dividing by 3, I have negative 2 is equal to x. And again, if we put in negative 2 for x, that equation will be true. So we have two solutions. We have 12 over 7, and we have negative 2. Now we're going to solve some inequalities. So let's first look at our solution for the absolute value of x equal to 4. So recall that that was negative 4 and positive 4. We just had the two solutions, so I could write it as a solution set, negative 4 comma positive 4. But what if we had the absolute value of x less than 4, or the absolute value of x less than or equal to 4? So let's think about this. Well, let's start with 4. Can we use 4? So the absolute value of 4 is 4. So that would read 4 less than 4, which is false, because it's strictly less than. So I can't use 4. If I use any number higher, that would be too big. However, what if I put in 3? The absolute value of 3 is less than 4. That's true. I can use 3, I can use 2, I can use 1, I can use 0. In fact, I can use anything between 0, 1, 2, and 3. And these would be solutions. What about negative? What if I put in -1? Well, the absolute value would be 1. 1 is less than 4, so yeah. I can use -1, -2, -3. I can't use -4 because I'll get 4 less than 4, which is not true. But I can use anything between -4 and 4. So it would be this open interval, if I was using interval notation, from -4 to 4. Which means my solution is going to be an interval notation since I don't have distinct values that I could list. Now, if I was to write this as an inequality, it would be x values between -4 and 4, so it would be -4 less than x, which is less than 4. So I can write this, oops, I have these curly braces, sorry, that should have been a parenthesis. So I have the solution written as an inequality, and I also have the solution written as interval. What happens if x is less than or equal to 4? Well, it would be the exact same interval as the above, except for now I can include 4 and I can include -4. And it would be everything in between. So in this case, that would be the brackets. And the interval notation would be a bracket, -4, comma 4. The inequality would be -4 less than or equal to x, which is less than or equal to 4. So what makes sense when you look at those inequalities, that if you have a less than or less than equal to with absolute values, and here we're going to look inside this box below, it makes sense, and here again we have k positive, that you would just get rid of the absolute values and put that quantity in between the negative and the positive k value. It would be the same if it was a less than or equal to. You would put that absolute value, what was in the absolute values, between the negative and the positive k values, but this time it would be a u greater than or equal to and less than or equal to. Now, there is a caution I would like to bring up now because it'll come up later as well. That when you talk about value, so this case I'm looking at that u, and this is a compound inequality. When you talk about values between inequalities, this is an and statement, which means it's an intersection. Okay. So when we say -4 is less than x, which is less than 4, that actually means, if I was to take this into pieces, that says x is greater than -4 and x is less than 4. So it means x is greater than -4 and x is less than 4. So the key is that that is an and, it's an intersection. So let's go ahead and graph the x greater than -4 and the x less than 4 separately so you can see what I mean. If I have x less than 4, that would not include 4, but it would be everything to the left. So this would be a parenthesis, and our interval would be -∞ to 4. If I were to graph x greater than -4, so it's -4 not included, but everything larger than -4. So again, that would be a parenthesis, and the interval would be -4, infinity. So let's look at -4 less than x less than 4, which is what we're saying the solution should look like. It's an and statement because we're seeing where those two intervals prior overlap. And they overlap, so these would be the elements that they have in common from -4 to +4. So it goes from -4, oops, I don't want that, -4 to +4, and since it was parentheses, it stays as parentheses. We get our interval, -4 to +4. But really what that is equal to is it's equal to the prior intervals. So -infinity to 4, but we're intersecting them. So this is going back to our set notation in R1. So we're looking at these two intervals and we're seeing what they have in common, where they intersect. And both of these intervals are correct. This longer one is correct with the intersection symbol. It's just not written in the simplest form. So when we do intersect those two intervals, the simplest way to write it is -4 to +4. Right? So again, value between inequality symbols is an and, it's an intersection. And again, you'll see why later why I'm kind of stressing this. Let's go ahead and solve though. Example 4a, we have absolute value of 2x minus 6 minus 5 is less than 3. So it doesn't quite look like what it needs to look like. I need absolute value less than some positive number. So I'm going to first try to get the absolute value by itself, similar to what we did when we had equal, by adding 5 to both sides to get this absolute value is less than 8. Now I have it in the correct form, absolute value less than a positive number. I can split it up to the 2x minus 6 between the -8, and since it's a less than, it stays less than, and the +8. At this point, I just need to isolate the x in between those two inequalities. So the first thing I'm going to do is add 6 to all pieces. If I add 6, this becomes -2 is less than 2x, which is less than 14. And the last thing I want to do is divide everything by 2. So if we divide by 2, I get -1 is less than x, which is less than 7. So here's the caution that I'm going to have, and we're going to go all the way back up. Whenever you're multiplying or dividing by a negative number, remember to flip the inequality sign. So we just did a division. We're going to go back. But we were dividing by a +2. So we didn't have to worry about flipping the sign. But now we have our solution. It's written as an inequality. If I were to write this as an interval, it would be the interval -1, comma 7, and since it's strictly less than, it's going to be parentheses. And one more, we'll look at B. Again, I don't know how I can get rid of these absolute values until I isolate the absolute value, keep it by itself on one side of the inequality. The first thing I'm going to do is subtract 3. Now remember, subtracting numbers from both sides of an inequality does not mean you have to flip the inequality. I'll have 2 times absolute value of 1 minus 4x is less than or equal to minusing 3 by both sides gives me a 26. So at this time I still have that 2 in front of my absolute value. I would then divide both sides by 2. Since I'm dividing by a +2, I don't have to flip the sign. The 2's just cancel. And I will have absolute value of 1 minus 4x less than or equal to 13. So absolute value less than or equal to a positive number, I can break it up into -13 less than or equal to 1 minus 4x less than or equal to +13. So breaking it up in between the negative and the +13. Now in this case, I would subtract 1 from all parts to get a -14 less than or equal to -4x less than or equal to 12. So all I'm trying to do is isolate the x in between the two inequalities, and I'm going to show the division for this one because I'm dividing by a negative number. So if I were to divide everything by -4, I would have a negative 14 over negative 4, which would simplify to a 7 over 2. I have to flip the sign. So instead of less than or equal to, it becomes greater than or equal to x. Flip the sign, greater than or equal to 3. Or I'm sorry, negative 3. That is correct, but typically we don't write our inequalities in that order. Remember, we're going to translate this inequality to an interval, and intervals are always small to large. So if I flip this around, this says negative 3 is less than or equal to x, which is less than or equal to 7 over 2. So now I'm going small to large. And it's a less than or equal to, so I'm going to use the brackets and translate this to the interval negative 3, comma, 7 over 2. And these are brackets. So don't forget to flip the inequality if you're multiplying or dividing by a negative number. Now let's look at what happens when the absolute value is greater than or equal to some positive number. So as a review, we're going to look at the absolute value of x less than 4. So what we did previously, recall that solution would be the interval from negative 4 to positive 4 and everything in between. If we were to write that solution as an interval, it would be parentheses, negative 4 to positive 4 parentheses. And if we were to write that interval as an inequality, it's negative 4 less than x less than 4. In the absolute value of x greater than 4, all we've done is we've flipped the inequality. So essentially, if you flip the inequality, you're also going to flip your solutions, which means that the solutions, instead of being between negative 4 and 4 or within, they're going to be outside of that interval. Let's go ahead and just put some values in, and we'll start at 4. If I were to put 4 into the inequality, I would get 4 greater than 4, which is false. But if I put in any other number larger than 4, like 5 or 6 or any numbers in between, that would make the inequality true. So absolute value of 5 is 5, that's greater than 4, that's true. And all the numbers larger than 4 will work. Now 3, 2, 1, 0, and all the numbers in between, those won't work because I'll get something that's less than 4. So the inequality will be false. And that would be true for negative 1, negative 2, negative 3, and negative numbers in between those values. So we'll go to our negative 4. Absolute value negative 4 is 4. 4 greater than 4 is false. So that doesn't work. However, all the negative numbers smaller than, so as we go left, we get smaller than negative 4 do work because their absolute value would make them positive and they would be greater than 4. So it did exactly what I thought it would do. It flipped the solutions. So instead of having solutions between negative 4 and 4, we have solutions outside of that interval. Let's go ahead and translate this to interval notation, and then we'll look at it with our inequalities. So our first interval is negative infinity to negative 4 with parentheses, and we have another interval which starts at 4 and goes to positive infinity. And this would be a union. What that says is I can choose any x value from the interval negative infinity to negative 4, or, because remember union is or, intersection is and, or I can choose x's from 4 to infinity, and that will also make the inequality true. Let's translate these intervals to inequalities. So the first negative 4 or negative infinity to negative 4 would be x's less than negative 4. That's how I would describe this. And 4 to infinity would be x's greater than positive 4. I cannot combine this into one inequality. It has to stay separated with or, and we'll discuss that in just a bit. Let's first go to the next inequality, which would be the absolute value of x greater than or equal to 4. The only difference between that inequality and the one above it is that I'm now including 4 and negative 4. So it would be the bracket, and everything larger than 4, bracket, everything smaller than negative 4. Switching this to interval notation, we have negative infinity to negative 4 with the bracket because we're including the negative 4, or would be the union, bracket 4 to positive infinity. Switching that to the inequality, this is x is less than or equal to negative 4. The union symbol becomes the word or, and that's important, it has to stay there. X is greater than or equal to 4. So again, we can't combine the inequalities. We have to keep them separated because when you look at those intervals, they are separated. So what would happen if you went ahead and wrote it in between the inequality symbols? For example, notice that this x less than negative 4 is here. X less than negative 4. And the x greater than 4, or greater than or equal to, is the x greater than or equal to 4. So if you put the x between the negative 4 and 4 and just flip those inequality signs, remember, values in between inequalities means and. So this is actually an intersection. It's x less than or equal to negative 4 and x greater than or equal to negative 4. So let's go on to that number line. What this is saying is that the only solutions, the only x values that will make that inequality true is if those x values are in the first interval and also in the second interval. They have to be in both. And there is no x that is in both of those intervals. So if you did write it that way, what you're saying is the solution is the empty set, which obviously is not true. We have a solution. We have two intervals with solutions. So that would just be the caution on that. However, let's move on. Let's say that you can write an absolute value less than some positive number, or sorry, greater than some positive number, or greater than or equal to some positive k value. Then you can split it up how we just split it up, with a greater than the positive or the less than the negative. Greater than or equal to the positive or less than or equal to the negative. We'll practice that in example 5. Part A, we have an inequality greater than negative 5. So does this fit the criteria? I don't know. I have to get the absolute value by itself. First thing I'm going to do is I'm going to add 14. Again, I'm not going to show that step. I'm just going to go ahead and add 14 to both sides to get greater than positive 9. And then I'm going to divide by 3 to isolate the absolute value and get greater than 3. Now I have absolute value greater than positive number. I could separate it into x. Oops. If I could write, I could separate it into x minus 7 greater than 3, or x minus 7. So it stays the same, but then we flip the inequality and we change the positive 3 to a negative 3. So change everything. So the x minus 7 greater than 3, or x minus 7 less than negative 3. And then we'll go ahead and solve these separately. First one, if I add 7 to both sides, I get x is greater than 10. Or if I add 7 to both sides, I get x is less than 4. Writing the solution in interval notation. Now we're done. This is the solution written as an inequality. Now we're going to translate that to our interval notation. So x greater than 10 would be the interval with parentheses 10 comma infinity. And the or becomes the union. X less than 4 would be negative infinity to 4 with parentheses. And typically we write from small to large, so I would actually rewrite this as negative infinity to positive 4 union, or 10 to positive infinity. So notice if we go from the left to the right, we have negative infinity, 4, 10, positive infinity. All those values are going from small to large, and that would be the solution. Try this again in part B. Again, it's not absolute value greater than or equal to some positive number yet. I have to isolate the absolute value by subtracting 7 from both sides. And remember, when you subtract in an inequality, you do not have to flip the sign. It's just multiply or divide. So this becomes greater than or equal to a positive 5. Now I have absolute value greater than or equal to a positive number. I can split it up into 1 minus 4x greater than or equal to 5, or 1 minus 4x less than or equal to negative 5. Solving separately, if I subtract 1 in the first inequality, I get negative 4x greater than or equal to 4. And I'm going to show the division because it helps me remind myself that I have to flip the inequality because I'm dividing by a negative number. So when I divide by this negative 4, I'm going to get x is less than or equal to negative 1 because I have to flip the sign. Oops. Now working on that second inequality, again I'm going to subtract 1 from both sides to get a negative 6. And then again, dividing by the negative, I'm reminding myself that I have to flip the less than or equal to greater than or equal to. Negative 6 over negative 4 becomes a positive 3/2. Don't forget to reduce and simplify all your fractions. And this was an or. Translating this to intervals, x less than or equal to negative 1 would be the interval from negative infinity to negative 1 with a bracket. The or becomes the union. Greater than or equal to 3/2 would be bracket, 3/2, comma, infinity. Now notice in this case, I am going from small to large. Negative infinity, negative 1, 3/2, infinity. So the order's fine. As with solving equations with absolute values, we tend to have an issue when we have 0 or a negative number. And that's true with the inequalities as well. However, there's more cases to cover. So let's just look at specific example. Example 6a, we have an absolute value, x minus 4, that's less than a negative number. So recall that absolute values are never negative, right? So this piece here, this x minus 4, it's never going to be less than negative 1. For some reason, this is not right. So this can't be negative. So since this will never be less than negative 1, it'll always be either 0 or a positive number. There's no solution. In part B, same thing, but now we have less than or equal to negative 1. Well, again, cannot be less than negative 1. But absolute values can never equal negative 1. They can never equal a negative number, right? They're always 0 or positive. So this is also no solution. Now look at what happens when we have a less than 0. Think about this. If I put in 4 for x, let's just do this. If x is equal to 4, then this is the absolute value of 0, which is 0 less than 0. And that's false. 0 is not less than 0. But if I put in something larger than 4, say 5, then I get 1 less than 0. 1 is not less than 0, that's false. What if I put something smaller than 4 in, like 3? Then I get the absolute value of negative 1, which is positive 1. And I also get false. It turns out that nothing works. because the absolute value is either equal to 0 or it's positive. It's never less than 0. Again, we have the empty set. Part D, that's the only time we're actually going to have a solution. And that's because of the less than or equal to. Absolute values can equal 0. So in this particular case, all we're looking for is the x value that makes this 0, which would be 4. So if x is equal to 4, I have 0 less than or equal to 0. This is true. And I have one solution, which would be 4. Let's just look at this. Less than or equal to negative number can't happen. Strictly less than 0 can't happen. Less than or equal to 0, that's the only case where you have one solution. So if we flip the inequality sign, we're probably going to flip the solutions or get close to flipping the solutions. So in A, we had no solution. So E is could be all solutions or something close to that. Let's look at it. Okay, we have an absolute value greater than -1. Again, I don't really care what's in that absolute value. All I know is that it doesn't matter. When I take the absolute value, it's always equal to 0 or positive. 0 is greater than -1. Positive numbers are greater than -1. So an absolute value strictly greater than a negative number will be all solutions. Negative to positive infinity. I can put in anything, and that makes sense because the other one was no. So flipping it, I get all. But we do have to be careful. It might not be in some cases. So in B, we had no solution. So F is probably going to be all or maybe close to all. So an absolute value greater than, now we have the or equal to a negative number. In this case, it's -1. So again, absolute value is 0 or positive. So it's always greater than or equal to a negative number. And in this case, it's just -1. So we get all numbers. And you could put in numbers for x, and you'll find no matter what you put in, it's always going to be greater than or equal to -1. So what about 0? Absolute value strictly greater than 0. Well, in the prior inequality, we had no solutions, so it could be all solutions, or it could be one solution. Don't know. Okay, so absolute values are always positive, so they would be greater than 0 or equal to 0. All right, so what if we had, say, x equal to 4? That would be 0 greater than 0, which is false. Okay, so any other x that I put in there is going to be positive, so it will be greater than 0. So if I put in 4, the inequality is false, but if I put in any other numbers, the inequality is true. So in this case, we cannot use 4. Okay, because 4 makes the inequality false. We're looking for x's that make the inequality true. That means in interval notation I can use anything from -infinity to 4, parentheses, or, so union, anything from 4 to positive infinity. So again, if I put in 4, that's false. If I put in any other x, it's true, and we're just looking for x's that make the inequality true. So that's a tricky one. But what about greater than or equal to 0? So again, all absolute values are greater than or equal to 0. So it doesn't matter what x I put in, this will always be true. So that would be -infinity to positive infinity. The last thing I would like to talk about, and now in your textbook, you'll notice that it covers a lot of graphing of absolute value functions as well in this section, and I chose to ignore that because we did a lot of graphing in the prior sections of absolute value functions. But what I would like to end off with is the formal definition of the absolute value function. So as you've seen before, whenever we had this equality of the absolute value equal to something, we always have both a positive and a negative solution. So if we look at this definition, it says if we want to get rid of the absolute value symbols, we just drop them as long as the value that's inside the absolute value is greater than or equal to 0. So if whatever's in there is greater than or equal to 0, we just drop the absolute value, right? So if we had x equal to 3, then the absolute value of 3 is simply 3, because 3 is greater than or equal to 0. However, if what we're putting into our absolute value is less than 0, so it's negative, then to get rid of the absolute values, we take the negative of whatever that is. So if we're just looking at the definition, and we're looking at x equal to -3, then the absolute value of -3, now we all know that that's just 3. But the thing is, why is it just 3? Well, formally, looking at the definition, it's because this is equal to the negative of -3, which turns to a +3. So that's actually what we're doing when we say, oh, just make it positive, is we're taking the negative of a negative, which turns into a positive. Now, typically, we don't really use that definition that much. Oh, but I did want to point out one thing. Notice that this absolute value function is defined in 2 pieces. Whenever you have a function and it's defined in pieces, we actually call this a piecewise function. And the reason why I'm bringing this up is because in 2.5, we're actually going to be looking at piecewise functions. So it's good for you to see this now, that all the piecewise function is a function that's defined in pieces. Let's move on to example 7. So why do we actually need this definition? Well, if we were to write these expressions without absolute values and we're not using a calculator, part A, that's not so bad. That's going to be equal to the absolute value of 2 times, now 3 minus 10 is -7. So I get the absolute value of a -14. And I could use the definition to write -14, which becomes +14, but we all know that this is just +14. So I really didn't need to use that definition. But let's look at part B. Now, if you were to plug this in a calculator, you would get a decimal approximation. It would not be the actual value of the absolute value of pi minus 5. Here we have to use the definition. So what we want to do is we want to look at pi minus 5 and ask ourselves, is this greater than or equal to 0? Because that would be, in our definition, that would be our x value. So is pi minus 5 greater than or equal to 0, or is it less than 0? Now you could put in this in a calculator and you would get some negative number, which would be the approximation. However, remember, pi is approximately 3.14, so if I subtract 5, I'm going to get a number that's negative. So I can see that this is less than 0. And because it's less than 0, I can get rid of the absolute values without using a calculator by using the definition. This would be equal to the negative of whatever is inside the absolute value. So we're taking the negative of all of that. And I got rid of my absolute values. However, this is not really simplified. So I'm going to go ahead and get rid of the parentheses by distributing the negative to write negative pi plus 5. I didn't use a calculator. This is an exact answer, and I no longer have absolute values. So if this were equal to something, then that's how I would get rid of my absolute values. Oh, let's look at something else. What if I were to change the order and write this as 5 minus pi? Because sometimes having a negative in the front of an expression looks a little weird. Look at what we started with. Whenever you're subtracting quantities, and whatever you're subtracting is negative, then to get rid of the absolute values, all you're doing is just changing the order and dropping the absolute values. So fun fact, but let's move on. Let's say that in this, now let's go back to our absolute value. This, remember, if we're looking this as a function, f of x equal to the absolute value of x. But now what happens if we take the absolute value of a function? So instead of having the function equal to an absolute value, we have the absolute value of a function. So what I've done is just simply replace the x's in the definition of the absolute value with f of x. So we have the absolute value of f of x instead of x is equal to f of x if f of x is greater than or equal to 0, right? So again, I'm just replacing x with f of x everywhere. And negative f of x if f of x is less than 0. And recall that our f of x is simply our y value. So if we take the absolute value of the function, these are y values. Remember, absolute value makes everything 0 or positive. That just means that graphically, all of the y values below the x-axis will flip up and become positive, and they'll be above the x-axis. We're going to look at that idea in example 8. We're going to use this graph, and this is our function f of x, to graph the absolute value of f of x, and we're also going to state the domain of both f of x and absolute value of f of x. Before I even graph absolute value of f of x, I'm going to take the domain, or write the domain and range for f of x before I start drawing all over it. So if I look at this graph, I can see that my first x value will start here at -4. And then it's continuous, there's no breaks until the x value of +3, which tells me that my domain, which is our x values, that would be going from bracket -4 to 3, and it's a bracket because that was solid. All right, now let's look at our range for this function. So again, the range would be the y values, and when I look at this graph, the first y value I see would be a y value of, it looks like -1, and there's a -1 here too. So -1, again, to see that, you would just look at where you first hit the y-axis, and that would be when a y value is -1. So it looks like my range is going to go from -1, and it's a bracket because it exists, and then the highest y value, the highest point on the graph, corresponds to +3. So this is going to go to 3. Oops, I want blue. I have found my domain and range for f of x. And now I'm going to draw all over this graph when I draw my, let me erase some of this, when I draw my absolute value function. So if I were looking at the absolute value of f of x, all that's saying is that wherever you have negative y values, you're going to make them positive. So we have this negative y value, and I'll change the color to green, that I'm going to flip up and make the -1 a +1. Now, all the positive values will stay where they are, right? That's the definition of the absolute value. Anything positive stays. The zeros stay. But all these negative values would flip up. The 0 stays. Negative values flip up and become positive. And then here we have this -1 flips up to a +1. All these negative values will flip up. So when you have a graph of a function and you want to graph the absolute value of the function, all you do is simply keep the graph that's above the x-axis the same and flip up all the stuff below the axis. Let's look at our domain and range for the absolute value of f of x. So the domain, again, those are our x values. That didn't change. And the reason it didn't change is because we are changing our y values by flipping the graph, but the x values remain the same. We're still looking at x values from -4 to +3. It's the range that changed because we flipped up those y values. So our first y value is 0, and then our largest y value remains as 3 in this case. And that's it for this section.